Hello everybody and welcome to this video. And as I promised you in the previous video, I always give promises and I always fulfill my promises. I'm going to show you some examples, some really easy examples to understand more or get a better intuition how deep learning, specifically neural networks, work with simple architectures. So in this video, we are going to talk about nonlinear classification, have some problems with nonlinear classification to solve, and the AND example and the OR example. What do I mean by that? It's just like the logical gates, if you know them. If you don't know them, we're going to see them on the way. So in this example, the non-linear classification example, what do we have? We have x1, x2. If y equals 1, then x, and if y equals 0, we have the blue O, like that. So that's the AND example. What do I mean by that? That it's a logical gate. So 0, 0, that means 0 and 0, that's 0. 0 and 1, that's 0. Why? I guess you already know programming. So if you have false and true, that means it's false. That's some logic. If you don't know it, I really recommend to study some linear algebra and logical gates and truth table. This is called truth table to understand exactly what I'm talking about here. So 1 and 0, that's also 0. So all these are zeros, and 1 and 1, when x2 and x1 equals 1, that means 1. That's an example for non-linear classification. Why it's non-linear? Because you cannot get like it's like 0 or 1. It's you cannot really get a linear classifier to do that job for you. And this is just like this example is actually just a small example from for example, if when we had the tumor, benign or malignant example, there was like many x's here and many o's here. So this is just a small example of the bigger example, which is a tumor classification. So let's see how to do that AND classification using neural networks. So x1 and x2, they always equal 0 or 1. They're always 0 or 1. So it's logistic regression, as you know, if you know machine learning, traditional one. So we have two inputs. They are x1 and x2. As we did before, we give them to a unit or a cell to process this input, and then the unit gonna have an output. And of course, we cannot forget our little bias over here. So how can we make this cell output output exactly the truth table we saw before here? We saw truth table here, this truth table. This is our goal actually. We want to get these exact values as an output because we want our cell to calculate the AND. So how to do that? Simply, as we saw in machine learning and deep learning, they're all depending on getting the right parameters. What do we mean by parameters? The bias and the weights. These are our parameters. So we want our neural network to learn the parameters to give us the right output. So after some learning with the sigmoid function as an activation function, if you remember the sigmoid function, so with the sigmoid function as our activation function, I did the math that we are going to learn how to program later. in the next chapter. So I did the math and I got these parameters, for example. So what does these parameters mean? We saw how to calculate the how to do the computation for neural networks, and so let's do it in this real example. So the first computation we have to do is multiply x1 by 30 because it's the weight, and x2 by also 30 because it's the weight, and then plus the bias. That means plus minus 40. That's minus 40. So we have 0 and 0. So that means that's 0. So we can delete all of that. And the x2 is also 0. So we can delete all that. We are left with minus 40. So, so we have as an input here minus 40. And then we have a sigmoid function. Then where is minus 40? Actually, I didn't write in the slide this, but this value here is almost, I think here, this is almost like 4.6, and this is almost minus 4.6 because it's symmetric. So if I say minus 40, it's like really way here, like really way. So the value of the sigmoid is way down than 0.5, that it's almost 0. So the prediction of our h of x, our hypothesis function, is going to be 0. That's right. So then we have x1 equals 30, x2 equals 30 minus 40. Also the same, but this time x2 equals 1. So this is what's different. x2 equals 1. So let's see, when x2 equals 1, that means we have 30 minus 40, that's minus 10. Minus 10 is also close to 0. Actually, it's less than 0.5 if we give it to the sigmoid function. So that means our function gonna predict 0. And then x1 equals 1, x2 equals 0. We are left also with minus 10. The prediction is the same, 0. And then we have 30 multiplied by 1, and 30 here multiplied by 1. That's all. That's when we add them together, that's 60 minus 40. That's 20. 20 is right here, like it's really above 0.5. So our prediction is going to be 1. So 20, and the prediction is 1. And that's how we built our first neural network to do the end classification, to predict the end value of x1 and x2. It's like a logic gate. We built a logic gate using neural networks. That's really great. So let's see another example, the OR example. x1 or x2. So we have our x1, x2, we have processing cell and the bias, and then we want an output that give us the right truth table for the OR logic gate. And we are, of course, going to use the sigmoid function we always used before. So, as we said before, the trick about neural network is change the values of the parameters. So the values now that when I did my math, as I told you, we are going to see that later, I got these values. So now we changed nothing about the architecture of the neural network. We just changed the parameter values, these values. So how the output is going to change? First, when we do when x1 and x2 equals 0, we are going to be left with the bias, which is minus 10. Minus 10, it's way down here, so it's going to predict 0. And then here is the change. When x2 equals 1, x1 is 0, so we are left with 20 minus 10, that's 10. 10 is way up here, That means it's going to predict 1. And then the same with the if x1 equals 1 and x2 equals 0. And of course, if x1 and x2 equals 1, both of them, we are going to predict 40 minus 10, that's 30. 30, put it through the sigmoid function, that's almost 1. So the prediction is 1. So now we built a logic gate of OR function using our neural network, actually only one cell, and the same architecture, just modified the parameters, and we got totally different output. So that's the great thing about neural networks. So in next video, we are going to see more complex examples building on the examples we already have seen, and making like more complex example. So thank you very much and see you next video.